So, I want to go over some notation first of in queuing theory. And basically what's going to happen, maybe I'll draw a real simple example of a queue. You have stuff coming in to a queue, and this symbol, this open symbol, where it's not a finite set of boxes, means that the queue is infinitely long. And then you go to, they generally draw a round ball to mean the thing that's doing the service, and then you come out of the queue. So, we want to know how much time when we go to visit the queue, we want to know how much time does it take for us to get from the point where we are arriving to the queue to the point where we exit the queue. So what's going to affect that? Well, a couple of things are going to affect that. How much stuff is in the queue when we arrive? Where is our position in the queue? Like if it's a first come, first served queue, then we'll be put in the back of the queue. In a little bit more complicated examples, we might move to a different spot. If it's like shortest job first, then we might, if we're a short job, we might jump to the front. If we are a big job, then other jobs arriving after us might be jumping in front of us. But a pretty straightforward one is first come, first served, the queuing discipline. So how much stuff is in front of us, we have to wait for that to be serviced. And then finally we work our way to the front of the queue, and then we get serviced, and then we're done. So, for the queuing system, we want to know a few attributes. We want to know, I'm going to use a couple of Greek letters here. It's just traditional to use lambda as the rate at which stuff arrives to the queue. So for example, lambda for this queue could be 2 per second. A rate is always an amount divided by time. Okay? Another thing we want to know that's going to affect how much time we spend here is how fast is this thing servicing us. Let's say this is a disk drive or a cashier at a supermarket. It doesn't really matter, but it's the thing that's providing the service, the thing that's getting the jobs done. So we want to know how fast is this thing going. And that will also be a rate. And we'll use the Greek letter mu to say it can handle, it could work at a rate of 3 jobs per second. Let's say hypothetically. That's the speed that this thing would work if you constantly fed it work. If the queue happens to have no customers in it, it'll sit idle. But if you constantly fed it work, it could work at a rate of, I'm just making up numbers now, 3 jobs per second. Let's say. Then we'll use the symbol T little s to mean the mean service time. That would be the time it took you from when you entered the system until you left the system. Another interesting statistic would be the Greek letter rho. And in this case, we're saying rho is equal to lambda divided by mu. What rho ends up being is the percentage of time that this device is doing something. So with these numbers I've made up, with a lambda of 2 per second, 2 jobs are arriving per second, this thing, if it was fully utilized, can operate at a speed of getting 3 jobs per second out. So what percentage of the time, the percentage of the time that this thing is in use would be 2 divided by 3, or 67% of the time. So just to say that again, if jobs are arriving at a rate of 2 per second, and this device can bang out the work if it was fully utilized at a rate of 3 per second, so it's faster than the work that's arriving. 2/3 of the time it's going to be doing something, 1/3 of the time that whole queue is going to be sitting empty and this thing has nothing to do. Then we use little q to mean the mean number of jobs that are in the system. Maybe I'll put an X here to symbolize something's being operated on, and 2 X's here meaning 2 things are in the queue. Okay, so we could use a little q and big Q could end up meaning something along the lines of how many are in the system at a given point in time, either being serviced or waiting. The response time is going to be the time from when you enter the system till the time you finish. And we said before, we said the mean service time is, that's how much time you would spend in service, which means being served by the device. Okay, the throughput of the system is how many jobs could this system, how many processes does the system get done per amount of time, divided by some amount of time. If the system, now we'll start looking at systems that have more than one service point. So let me just briefly talk about that. And let's say hypothetically, let's leave this up. If after you come out of this queue, you go into another queue. And then maybe after you come out of this queue, you could go back into the first one, or maybe you finish and exit the system. So here's where you would enter the system. You would go through this queue, and then when you're done, you go through a second queue, and then maybe you leave, or you go back to this first queue for another loop. Let's say something like that was happening. Based on the rates into the queues and how fast the servicing node services, one of these two devices is going to get closer and closer and closer to 100% utilization. Right? If you, in other words, if you kept increasing the amount of processes coming into the system, eventually one of these devices is going to get closer and closer to 100%. Once one of these devices hits 100%, meaning there's more work coming into it than it can handle. Right? Like we said before, let's say this thing services, the speed at which it processes services is 3 per second. If you ever got to the point where you were pushing in 5 things per second, it'll never keep up, right? So the utilization of that device will hit 100%. It'll constantly be working, and then the queue will theoretically grow out to infinity because more work is showing up than it can handle. So out of all the devices, the device that ends up hitting 100% utilization first is what we're going to refer to as the bottleneck device. Once we have a collection of queues, a path that processes travel through from queue to queue, once we identify which service node of the queues will get to 100% utilization first, that's the one that's going to cause our whole system to stop. If that one ever hit 100%, we'd have to stop. Or we'd have to stop allowing more processes to enter. So it's going to be important as we get to bigger queuing systems to be able to identify which one is the bottleneck device. So the bottleneck device is the device that will hit 100% first. A system, which is a collection of queues, if it gets to the point where the bottleneck device has hit 100%, we cannot add any more processes to the system. Otherwise, that bottleneck queue will expand off to infinity. So we call, once the bottleneck device is 100% saturated, then we can't add any more to the system when we say that the system is saturated. If the bottleneck device hits 100%, the system is saturated. Okay, is there any questions about these definitions? Does it make sense that we would need to define these values in order to look at a queue to know how long it would take per visit to the queue? Okay. So now another notation we just want to get used to is sometimes referred to as Kendall notation. But this is when we want to describe, like the picture that I just drew, we want to describe what it's like. What's going on in the picture, we could describe describe it with a string that looks like this. That's like A slash B slash C slash K slash Z M slash Z slash. And, okay, so before I go into this, let me go over a queuing example. Suppose we had a queue that looked like this. So it's similar to the one we just had before. And I said to you, what I want to talk about is the A and the B right now. I said to you, jobs are arriving at a rate of 2 per second. So stuff is arriving to this queue at a rate of 2 per second. And the servicing node is can operate at a speed of 2 per second. Okay, so things can be serviced at a rate of 2 per second, and there work's coming in at 2 per second. If I ask you the question, at a random point in time, how many items are in the queue? Could you answer that question, or would you need more information? So think of it like this. 2 people are showing up to, let's say there's a convenience store, a deli, and 2 per second is a lot. Let's say 2 people are showing up per minute. And the cashier in the store works fast enough making sandwiches or whatever it is they're doing to be able to service 2 people per second, right? So the server is operating at exactly the speed that stuff is showing up. Server should be utilized 100% of the time in this case. But if I ask you a question, how many people would you say are waiting behind somebody? Could you answer that question? Or would you say, wait a minute, I need some more information? What's that? 1 would be waiting? Okay, why 1? Yeah?
Well, with the 2-minute example, you could have as many people as you want coming in the door, all one guy's being served. I mean, it works similar to the 2-second example. You don't know how many people are coming in as one guy's being served. So
well, all right. Can you? Yeah. Let me ask the question this way: is there a way that you could keep these numbers 2 per second, but if you had control over when people can arrive and not arrive, can you organize it so that nobody ever waits? So, for example, suppose people showed up at exactly once every second, at exactly that, when the clock hit exactly 1 second, someone shows up. And at exactly 1 second later, this service time is not only 2 per second, but to service each customer takes exactly 1 second. It's not like, well, it took 1.5 seconds for the first one, and then 0.5 seconds for the second one, and it kind of averages. I'm sorry, 2 per second. It's not that it takes a 1/4 second, so that would be 0.5 second for each one, right? If it can handle, that's one thing we want to get used to, the reciprocal relationship here. If it can do 2 per second, it on average takes 0.5 second per service, right? So we can have a situation where half the time, some of the time it takes less than 0.5 second, some of the time it takes more than 0.5 second, but on average it takes 0.5 second. We can have a situation where the arrivals are coming in, maybe 3 of them arrive at once, and then for the next couple of seconds nothing happens, but it averages 2 per second. Right? All we're saying here is that there's an average of 2 per second. So suppose we structured it in such a way that the arrivals arrive exactly once every 2 per second, once every 0.5 second. at every half-second interval, at exactly that moment the next person arrives. And the service takes exactly half a second each. Suppose that was the case. Then, how many people would be in the queue? At a random point in time, if you just looked at the queue, how big would the queue be? It's empty, right? Because as soon as we start, one person arrives, and then a half a second later, that one departs and a new one arrives. Half a second later, that one departs and a new one arrives. No one would ever be in the queue. But now suppose we didn't have that. Suppose that these are just averages. Sometimes you're in service, it could take 3 seconds. Other ones could take a quarter of a second, and it just averages out to 2 per second. And suppose the arrivals are kind of random, but with an average of 2 per second. Then the answer would be something higher than 0, right? Sometimes the queue will be empty and sometimes it won't, right? So the question, how many are in the queue at an average point in time, if all I told you was they arrive at a rate of 2 per second and their service at a rate of 2 per second, you could say, on average, this thing's in use 100% of the time. That sounds reasonable. But if I asked you how many are in the queue, you'd start asking questions like, how much time, what is the distribution between arriving events? Are they scheduled? Are they totally random? Are they somewhat connected to the guy in front of them? Like, is there a rule like you have to wait at least a quarter of a second before the guy in front of you, after the guy in front of you arrived, before you can arrive? So the gaps between the two are going to matter. So for a queuing system, we'll give a notation to the queuing system where we'll say, A is going to, the first symbol is going to mean the distribution between arrivals. The second notation, which we'll call B right now, is the service time distribution. Are these being scheduled? Are these being done one every half a second, or do they just average one every half a second? The third symbol will be the number of servers. The fourth symbol will be the size of the queue, if the queue is finite. We could have infinite queues or finite queues. If it's finite, we'll give the size of the queue. The fifth piece of notation will be the number of processes in the system. This would be if it's a closed system. And I'll draw a system in a second to show like this notation. And the last symbol will be the queuing discipline, like whether it's first come, first serve. So if we had a queuing system that, and I guess I'll explain this in a second, but if we said something like this, M, D, 3, 12, no, sorry, 3, 4, 12, first come, first serve. So if you saw this and you were told there's a queue that has ND 3, 4, 12, first come, first serve. What that would mean is this. We would have, I'll draw a picture of the queue. We'll have 3 servers. The queue will be size 4. So I'm going to draw 4 boxes. And this is finite. I don't have that open-ended thing. This is finite. There's 4 spots in the queue. If you arrive at this system and there's no room for you in the queue, you just go away. We only queue you up for a size of 4. So we come out of the queue and you go to the next available server. So it's kind of like if you go to a bank and the light comes on and tell her so-and-so is now available, you go to that one. If it's a closed system, so let's say, so we have 3 servers, 4 seats in the queue, 12, this is going to be a closed system, so 12, there's a total of 12 processes in the queuing system. So it's a closed system. There's 12 customers in here that just keep looping through forever. If the system was open, which we'll study both open and closed ones, open systems mean new processes can start up, run, and then leave the system. A closed system means there's processes that just run forever and no new ones can enter. So an open system, we wouldn't have the size this is closed systems only. We wouldn't have this number, so we'd just leave it out. But if it's a closed system, we would have that number. And then the queuing discipline is first come, first served. So when you arrive to the queue, you go to the back of the queue. We could change this to shortest remaining time first, or we could use different queuing disciplines here if we wanted to. Okay, so basically this is just notation. So like you could be given notation like this, and then in your mind you want to know this is what the picture looks like. Okay, so for example, what would, oh, so sorry. Let me explain what M and D are. M and D are the two most extreme distributions. So a D is typically meant that the arrivals are deterministic, meaning they're happening at exactly discrete intervals. So for example, if I said to you that the service time, which is deterministic, operates at a rate of 2 per second, and it is deterministic. So a D means the distribution is deterministic. That means if you put something in this server to be processed, it will take exactly a half a second. Never a little less, never a little more. It takes exactly half a second and it's done. Because it's deterministic. So it's at this rate, and the amount of time it takes is exactly the same every time. If the arrival rate, the other extreme to being deterministic, the other extreme is totally random amounts of time, has no connection to the previous event, no connection to the next event, it just happens whenever it wants to happen. But it still maintains a rate of 2 per second. This is called a Markovian distribution, and it models a Poisson process. I don't know if that's come up in any of the classes, maybe probability class. So anyway, just a very, very quick definition of what a Poisson process is. It's, I was going to write it out, but so this comes up a lot in queuing here, a Poisson process. So it's O-I-S-O. So have you heard the name Poisson before in some probability class? Or sometimes in network classes. It's a famous French mathematician. Last name is Poisson. And Poisson means, have you gone to a French restaurant? You ever see Poisson on the menu? You know what Poisson means? Fish. Fish, right, okay. So, if he was English, his last name would be Fish. So, but it's Poisson. So, the mathematics on this, but it's basically saying an event that occurs totally random, but obviously events have an average time. So, if if you were to roll a dice over and over and over, and you said to yourself, how often does a 5 come up? You'd expect it to come up 1 out of every 6 times, right? But would you expect it to come up every 6th time? No, it's totally random. You might get 3 in a row, then it might be 20 rolls before it happens. That would be a Poisson process. The events are not in any way tied to any previous or future event. It's totally random, but the rate still stays the same. So one extreme is that totally random. There's no connection between previous and future events. The other extreme is perfectly deterministic, once every 6 rolls, no matter what. And then the real world is usually somewhere between the two. So like if I said to you, people show up at a supermarket at a rate of 2 per second would be good, but let's say 10 people per minute. Would you expect it to be deterministic? So 10 people per minute would be once every 6 seconds, right? Would you expect the people to show up exactly every 6 seconds, or would you? It couldn't be perfectly Poisson, because then people would be knocking into each other coming in the door. Some people have to say, all right, you go first. So it's not quite deterministic. It's not quite cross-owned, probably in the real world it's a little somewhere between the two. But it's kind of interesting to study the two extremes and then realize your queuing system might actually not, might be deterministic, might be between the two. Suppose your thing that's doing the serving is a disk drive that has to move the read-write head out to a position, or it has to start up when the request comes in, and that's a fixed amount of time. And then how big the file is you're getting is totally random. Then what would the service time be? It would be a combination of deterministic and Poisson, right? So the real world ends up being somewhere between the two, but we'll study the two extremes because it kind of makes the math a little bit easier. So, okay, so another topic would be a topic called Little's Law, or a formula called Little's Law. And Little's Law basically says this: the number of customers in a queuing system is equal to the rate into the system times the amount of time you're waiting or the amount of time you're in the system. So an example could be a supermarket. Suppose the rate into the supermarket is 10 people per minute. And the amount of time a customer spends in the supermarket is, on average, 30 minutes. Now, I haven't told you if the distribution is like deterministic, meaning people show up once every 10, that's pretty fast, right? Every 6 seconds a new person shows up. That's kind of fast for a supermarket, but I'm not saying it's deterministic. I'm not saying it's Poisson. It might be between the two. I'm just saying it's 10 per minute. And the average person spends 30 minutes in the supermarket. Some spend an hour, some spend 3 minutes, but they average 30 minutes each. At a random point in time, if I asked you how many people are in the supermarket, could you answer that, or would you have to say, wait, it depends on the distribution? Well, according to Little's law or Little's formula, it would end up being n equals 10 per minute times, it should be 30 per minute, it's 30 minutes, equals 300 people. On average, would you agree with that or not agree with that? Would you say, well, it depends on how much time is between each person, and some people spend an hour there, and some people only spend 3 minutes. That could throw the number off. Would it throw the number off or not? So it's kind of an intuitive question.
It would be an approximation. It would never be exact. Except if I ran.
Well, no, it's not. I'm not saying that at every moment there'll be exactly 300 people. But the question is just asking, on average, if you picked a random point in time and said, okay, lock the supermarket and count how many people are in there, what would you expect the average to be? Could you say the average would be 300, or would it? Yeah.
When we say average, do you mean like Gaussian kind of average, like in a certain amount of time? That would be about 300.
Well, maybe I'm thinking expected. What's the expected value? Expected number of people in the supermarket at a random time. Obviously, sometimes it'll be less than 300, sometimes more. But is the statement it will on average be 300?
Yes.
Correct. Yeah. So, and it's regardless of the distribution of their, like they could all be arriving in bunches, and then at that time period there'll be more than 300. Then later on, because there's a lull in the, let's say at lunchtime, a lot of people arrive. So there'll be 600 at lunchtime, and then at 2 in the afternoon it might be 200, but on average it will be 300. And that would be independent of the distribution, the gaps of time between the two. Okay, and then actually I already did a utilization question. So suppose we had a queue that was, this is one example. Suppose we had another example. We had an MM1 queue. So what's an MM1 queue? An MM1 queue is a queue that has random Poisson arrivals with a certain rate, Poisson service time, meaning we have an average, but it's totally random. It could be a fraction of a second one time, a ton of time to do service another time, and we have one server. Since we have one server, since we have no size of the queue, it's assumed to be infinitely long. Since we don't have a fixed number of processes, it's anyone can arrive and then leave at any time. And the queuing discipline, another thing, the queuing discipline by default, if we never say what the queuing discipline is, then the queuing discipline is assumed to be first come, first serve. So, an MM1 queue, probably the most popular queue. If you go looking on Google and queuing theory, you probably see a lot of examples with MM1 queues. So it looks like this, it's an infinite queue. The arrivals are Poisson, so it's lambda equals, let's say 1 per second. And the service rate, mu, equals 2 per second. You always want the service rate to be faster than the work that's arriving, otherwise it can't handle it. Okay, so what would be the utilization? What percentage of the time is what percentage of the time is the device, the serving device, in use? So work is arriving at a rate of one job or one process per second. This thing works at a speed that it can handle 2 jobs per second. So what percentage of the time is the thing in use and what percentage is it? 50%. So that would be 1 per second divided by 2 per second. The per seconds cancel and we get 1/2. So half the time it's in use. Okay. Okay, let's say we had another queuing example where we had a situation like this. Suppose we had an infinite queue that had 2 sources of income, 2 sources of arrivals. And had 3 servers. And each of the servers individually, the mu for this one was 1/4, the mu for this one was 1/4, and the mu for the last one was 1/4. And the arrival rates were from this device. So this is really what we're starting to get into now is 2 different queues are going to be spitting out output, and then those queues will run into another queue. So really we're going to end up building like a big network of queues, and then the output of one is going to go into another one. So let's say this was coming in at a rate of 2 per second, and these were coming in at a rate of 1 per second. So what this is going to really end up being from a bigger point of view is some queue, we're going to calculate its throughput, it's spitting out jobs at 2 per second. Another queue is spitting out jobs at 1 per second, and then they're both coming into the same queue. So now what we'd like to figure out is what percentage of the time are these 3 servers in use? So what is the input, how much work is coming into the queue?
3%.
Right, 3 per second, right? All the inputs can just all be collapsed into one big input. So there's really nothing too tricky there. It's 3 per second. So really the lambda, the overall lambda, let's call this lambda 1, call this one lambda 2. The overall lambda is equal to lambda 1 plus lambda 2, which is 3 per second. Now, they line up into the queue, first come, first served. And then of these 3 servers, when one of them is done, it picks the next one out of the queue. So what we're trying to ask ourselves is for each of these servers, what percentage of the time are they in use? So the last example, we had a mu, meaning the percentage of the time, but there was only 1 server. Now there's 3. So what would we have to do with 3 of them? So the utilization would end up being, would be the overall lambda divided by the number of servers. Now we can only do this if they all operate at the same speed, but we can do this. So, actually, this should be, the mu's are rates, how many it can do per second. So these should actually just be 4s. 4 per second. So really, collectively, assuming the operating system is doing its job of distributing these 3 servers can collectively do 12 jobs per second, right? If run optimally, they could do 12 jobs per second. 3 jobs are coming in per second. Collectively, these can operate to do the work of 12 jobs per second. So what percentage of the time would they, on average, be in use?
25%.
Right, they would end up being, what would it be, 3 divided by 3 times 4 equals 25% of the time. So these would be, on average, in use 25% of the time. Okay. So you can kind of see where we're going with this. Basically, we can now take a network of a queue, spits out output, could run into another queue, could go back to the processor, which is just going to be another queue, because the processor has a ready queue, so stuff will queue up to go to the ready queue. Runs for a little while, then has to go out to the disk drive, that's a queue. After it's done getting the page it needs, it goes back to the ready queue. So they're just jobs that are just bouncing around from queue to queue, and then eventually it says, okay, I'm done. Hopefully your job eventually finishes. So suppose we had a queuing system that looks something like this. Here's another example. Suppose we had, this is a real simple, let's just say we had a processor and a disk drive. For a queuing example. And suppose jobs come in to our system, and the first thing they do is they start running on the processor. They run for a while, and then sometimes they have to go out to the disk drive to bring a page in. A page has to get swapped in. So sometimes they go from this queue. I'm not even drawing the queue, like the seats in the queue, just assume they're there. And then this is the disk drive. We go out to the disk drive sometimes, let's say half the time, we go to the disk drive. And half the time, we finish. And we are done. If we have to, so we go out to the disk drive because there was a page fault. We were running, we executed an instruction that's not in memory. We had to go out to the disk drive, bring that page in. That's going to take a certain amount of time. And then we start running again. So anytime we go out to the disk drive, we're obviously not done. So we come back to, let me put a little cube in front of this thing. We come back to here and we go back to the processor again. I don't put a cube in front here. Okay, so half the time, when we go to the processor, we get on the processor, we start running. Half the time we have to go out to the disk drive, wait for the page to come in, and then go back to the processor again. And half the time when we're on the processor, we are finished. We're done. We exit the system. Okay. If you wanted to calculate how much time do you expect your process to run, what would you have to do to calculate it? So here's what your process is going to do. It's going to, without a doubt, go on the processor, because that's the first step. It goes on the processor. Sometimes, we'll say half the time, the operating system is running statistics on processes that are running, and it notices that half the time a process is running on the processor, it finishes. No problem. It's done. And half the time, it goes to the disk drive, and then it has to go back to the processor and then kind of start over. If you wanted to calculate how much time on average does it take for a process to enter this queuing system, so there's 2 queues on it. The output of one queue, half the time feeds into this queue. The output of this queue, all the time, feeds back into this one. And the output of this queue, half the time, goes out to the outside world. If you want to know how much time from the moment you started, what we called before the throughput, no, I'm sorry, what we called before the service time, what we call the service time, from the moment you, I'm sorry, not the service time, the response time, the time from when you enter until you finish. The time it takes from when you enter the system until you finish, if we wanted to figure it out, what would we have to add up? We'd have to say how many times do we visit the processor? Okay? How many times do we visit the processor?
This phone's on silent. This one's silent.
Let's go.
I think
Okay.
press anything.
Okay, so anyway, if we wanted to calculate,
Sorry.
if we wanted to calculate how long it took from the moment we entered to the moment we were done, which is going to be an important statistic, what step would we be involved? We'd want to know how many times did we visit the processor, how many times would we expect to visit the processor, how long does each visit take? How many times would we expect to visit the disk drive? How long does each visit take? Add it all up. And that'll give us the average amount of time we took to do this job. So, we're going to use some of the formulas we had before to figure out how much time we spent here, how much time we spent here. But this is now a probability question. If you did something that took, if you did something like this, you went from half the time you went over here and half the time you left, and the times you went here, you had to go back to the first node again. So this is just a probability question. How many times would you expect to visit the disk drive? This is very similar to the probability question. If you had a coin that you flipped it, half the time it was heads, half the time it was tails, and you wanted to know how many times would you expect to flip the coin until you got the first heads? Does that question ring a bell? So it's pretty much the same question. How how many times would you expect to visit the disk drive in this case? Here's what the answer ends up being. 50% of the time you'll never visit it. 25% of the time you will visit it once, and then, no, sorry. 50% of the time you'll never visit it. 50% of the time you will visit it once, plus you start over again. So what's the expected number of visits?
25 to the end.
What's that?
25 to the end.
Let's say E was the expected number of visits to the disk drive. It would be 0. 50% of the time it will be 0, and 50% of the time it will be 1 plus you have to start over, which would be E expected number of times to the disk drive. Half the time you will exit and never hit the disk drive. The other half of the time you'll visit it once, and then you're really starting over again. Once plus whatever this number is. So the expected number of trips to the disk drive would be a half plus a half of E of D, which would mean a half ED equals a half, which means ED equals 1. So really what ends up being is half the time it'll be 0, a quarter of the time it'll be 1, an eighth of the time it'll be 2, a 16th of the time it'll be 3, and if you added it all up, on average it comes out to 1. How many times would we expect to visit the processor? That would be 1 more than the disk drive, because we're going to visit it once, and then after that, each loop involves a disk drive and a processor loop too. That's the way this one happened to work out. So the expected number of visits to the processor would be 2. For a job following this pattern, on average, you expect to visit the processor 2 times, the disk drive once. And then we just calculate how much time do we spend at each trip to the disk drive and the processor, add it all up, and that's the total